Hello YouTube viewers, welcome to my channel Science to Technology. In today's show, Future Friday, we're going to talk about CO2 battery or made from energy dome. So let's dive right into it. Yeah, the very weird name. So why do we need something like this, like CO2 battery? Well, reality is renewable energies are here in every country, every continent. Everybody is going into renewable. Why? It's cost effective, meaning at this point in time, it's far more efficient to build a gigawatt hour solar farm compared to a gigawatt hour coal system. So from cost point of view, everybody wants to go into renewable. We have it, and everybody wants to hear, just because it also gives you independence, energy independence, where you won't be dependent on national politics or international wars. It's like, what the hell, like electricity cost is going up. So that is really good. However, at this point in time, we do not have any renewables on large scale that is 24/7 base load, meaning it cannot give you a guarantee where it's like, this is me, I'm going to give you 24/7 this much amount of energy. We do not have base load capacity. Even solar, you may think, okay, sun will always shine. Yeah, that is true. But what about clouds? What about bad weather? What about humidity? All of those things will affect the output of those cells. So you could have a scenario where the farm that you're like, hey, this farm is like, let's say 500 megawatt hour. You may have a scenario, hey, it's only giving 400 megawatt, or maybe it's giving 300, or it may be not giving at all because there was like a giant eclipse. Things of that nature does happen. So that creates a scenario where our grid cannot sustain only on this. So same goes with wind farm also. Wind farms have like really bad up and down scenarios where their lower output could go very low, like few hundred megawatt, and higher output could go ludicrously high, like few hundreds of megawatts. So you could have a plant that is like 100 megawatt output, and sometimes it goes to 600 megawatt, and that creates a very weird scenario where energy companies have to shut down turbines because it's pumping too much energy into the grid. It happens, it's curtailment. It's a surprisingly common. Most people will be like shocked how many times wind farm has to be curtailed. So we have surplus energy, even from solar, even from wind. We have it at this point in time. And from cost economics, everybody wants to do it. It's just that we do not have any way to store that excess energy. The moment we do that, the end problem solved. So what kind of scale we are talking about? Like how much oomph we have to store? You are talking about something bare minimum touching gigawatt hour capacity, meaning let go of your megawatt. You have to jump into gigawatt hour, and you need hundreds of this to manage a country. So fundamentally, we need a lot of it. And then only if you achieve that, then we can achieve 100% green power generation without any issue. And from a country's point of view, many times people don't believe in global warming. No problem, don't believe into it. Don't believe into global warming, climate change, don't worry about it. Think of it this way: would you rather live in a country that is completely self-sufficient, meaning does not have to worry about importing coal from Australia, does not have to worry about getting gas from Russia, does not have to worry about getting oil from Kuwait or things of that nature? Would you rather have a scenario where you have like, oh, I'm dependent on these, or like, bro, I got this? Just from national security point of view, what would you rather have? A system where it's like, dude, no matter what you do, you can't block out the sun. No matter what you do, you can't stop a wind. So we good, we stable, we got this. So what would you rather be? So that's why there is a very severe need of it. So what is the principle of this CO2 battery? It's not a chemical battery. It's not electrochemical like lithium ion or things of that nature. It's a flat out mechanical system. So it's relying on what we call phase change between gas and liquid, exactly like your phase change refrigerator that we have in air conditions or refrigerator, things of that nature. So working fluid is changed to CO2. Yeah, that is the ironic part of it. And you have to understand, CO2 is like, there are companies that are selling you a refrigerator that is working on CO2. It's far less brutal to ozone layer compared to other gases. So people have chosen this also, but it does only work in commercial scale, not for low cost scale. So how do you charge it here? Well, charging simply means compressing the gas phase of CO2 into liquid. Now you're like, didn't I study in schools that CO2 will not go into liquid? Yes, that's in ambient pressure, meaning if you have 15 psi, normal 1 atmosphere pressure, nothing will happen to it. Nothing. It's just like, I don't care. Because if you have a solid dry ice and you just like let it be and it starts to heat up to room temperature, it will directly go to gas. But that will not be the case. If you take the same dry ice, put it into a container and lock that puppy in, meaning not a single atom can escape, does not have to be that tight, but you get the point. Like if it cannot escape, it will turn to liquid. So it does require pressure. It's almost like how we have LPG cylinders in our household, where it is a cylinder. If you can have a window through it, sight glass like that, you will see liquid here. Here's what will happen if you open it. Nothing. It will turn into gas. So it can remain in liquid phase as long as it's pressurized. So that's what you are doing. You're compressing that puppy. Now you can understand that will absorb energy. If you're compressing something, it will take energy to do that. That's the charging phase. Discharging is you are just evaporating. You're just letting it go run free. You are going from liquid to gas. That will drive a turbine. Now, this sort of system sounds very familiar, similar to cryogenic energy air storage, and yeah, it is the same logic. Only difference is it's a closed loop system. Now, closed loop is very necessary for efficiency. The moment you make something open loop, the efficiency goes YOLO. Cryogenic and air energy storage system is one of the best. I've already covered it, and so far that was the only technology that I could actually trust for providing few gigawatt hour capacity to worldwide. So, meaning every country can do that, be it Nepal, be it Pakistan, be it Bangladesh, be it India, be it Sri Lanka. But at this point in time, this technology appears even better because it's a closed loop system. That system has to suffer way too many losses because A, it has to drain air, it has to suck air in, okay, then it has to filter it. That itself will waste energy. After that, it has to displace other gases out of it, mainly oxygen. Then it has to, liquefy nitrogen. So you see that all those steps will waste energy. Now, like, what if we cycle the nitrogen again? You can't. It consumes too much nitrogen, so the bladder that you would need to store that nitrogen would be huge, as in idiotically, like even bigger than what this puppy is requiring. So it's not economically viable to store that kind of nitrogen. Consequence, every time you are charging that system, you are wasting energy in cleaning, separating gases. So round trip efficiency is really bad. And not to mention, going to very low temperature like liquid nitrogen temperature does not improve efficiency in some regards. Like, you really want things to be like in okay kind of temperature, not like too low, not too high. You want things to be in like okay kind of temperatures. So this puppy is closed loop. That gives it very high round trip efficiency, meaning if you put 1 megawatt of energy in, you should get very large amount of it out, meaning almost like, let's say, 800 kilowatts out. So it is also bonded with thermal energy system, because if you know anything about compression, the moment you compress something, it dumps heat, meaning there's a lot of it. That's why we use it in refrigeration. It just pumps heat from one place to another. How do I get compression? So if you're compressing a normal 1 atmosphere CO2 into liquid phase, that could require very high pressure. It will create a lot of waste heat. Now that heat, in general scenario, if you let it go, you will lose majority of your efficiency. Right there, you lost majority of your efficiency. You might not even do it, because at that point in time it's 25% efficient if you let that heat go away. So this system is bonded with TES. If you look at any of the graph, they say TES. That's what they are talking about, thermal energy system. And it is exactly same as cryogenic air storage system, where you have two systems that are taking care of the heat. Now, one system they have specified is water. Water is like absorbing a lot of the high temperature heat, and it's helping in two phases, meaning during charging, it will absorb waste heat. During discharging, it will help CO2 to get into higher pressure. Again, if you have the same volume of gas, you heat it up, it increases in pressure, same thing. So during charging, it's absorbing the waste heat. During discharging, it's pumping that heat back in to improve efficiency. Then they also have proprietary TES system, which is most likely is a stone base. Why it's stone base? Because again, that's the only temperature resilient material that I can think of. Again, it could be something else. My guess is stones. So it only works for large scale. Be very mindful. I'm talking about the system. It's, again, right now the scale is like 4 megawatt they have built, and they are working on 100 megawatt. That's the bare minimum. This sort of system actually improves in efficiency the larger you make it. So small ones, you will be lucky to get 80% efficiency. Large one, you can really push yourself and you can achieve 85% efficiency. And when you're talking about gigawatt hour kind of energy scale, saving even few percent does matter. So it's one of those things that does not scale well. You have to make it as big as possible. So water and proprietary, which I am assuming is stones, is their quote unquote magic bullet. That's fine. And because everything is closed loop, they should achieve very good round trip thermal efficiency. That's the principle of it. Let's look at the workings of it, how the heck it works. So dome is for storing clean CO2. Now this cannot extract CO2 from atmosphere. Atmosphere has very little CO2. So, and that's the problem aspect of it. Like, that little CO2 is like cooking us. We have to have a dome basically. Now that dome is basically one outside structure that is mainly for protection and thermal sensitivity, and there is a double bladder inside there. It's almost like a balloon, and that balloon is like equalized. So the cavity will not become vacuum when you're drawing it. It will be like, pressurized with normal atmosphere. Basically, there is a vent. So the dome will store your clean CO2, just raw CO2. Then that CO2 will go through the compressor. You will compress that, and this compressor will be driven by the motors when you ask it to. Meaning, if let's say a wind farm is going 600 megawatt production, grid requirement is less than that. Instead of turning off wind farm, there's like, okay, turn on this motor. And now that puppy will compress. It will absorb energy, compress this puppy. Now compressing that working fluid, meaning CO2, will generate lots of heat. That heat will be absorbed by the stone basin thermal energy recovery system. then it will go into condenser phase. That phase will basically cool it down even further, then it becomes a liquid. Now be mindful, it is a liquid, but it is a high pressure liquid, so it will be stored in a tanks. This is your charging phase. Now water has absorbed some amount of energy, and thermal energy system has absorbed the majority of the energy, and everything else is stored by the system. That's why inherently, in principle, if everything is perfectly insulated, you should reach 100% efficiency, but real world does not reach that, but that's why it's so high. Now during discharge, you will be like, okay, the pressure, you will open the pressure valve, that will go to the first evaporator unit. That evaporator using hot water will evaporate, then it will go to thermal energy system, that will dump even more heat into it, cooling it down, and then you will have very high pressure CO2 that could be as hot as 300 degrees Celsius, and then it will drive the turbine and you will have generator providing power. Done. Go home. And the excess gas that is coming outside of it, this is the core difference between cryogenic air storage versus this, is that it's going back in the bladder, and that's why it's a closed loop system, meaning there is no longer sucking air from the outside and filtering it, refining it, removing oxygen. No, it's just like a closed loop. It's a complete, basically it's like a giant ass refrigerator. And the proprietary thing they are claiming is that TES and the water bath. Again, these are things are mainly there for efficiency improvement. And now, is it as small as like a pumped hydro? Yeah, it's much smaller than pumped hydro, so the footprint would be smaller. Is it as dense as a cryogenic air storage? No, cryogenic air storage even more dense, but this has round trip efficiency. So if you have to choose between round trip efficiency, meaning I put 1 megawatt in, I get almost 800 kilowatt out, versus I put 1 megawatt in, I would be really lucky to achieve like even 600 megawatt. Yeah, flat out. From economics point of view, it's far more efficient to have something that is efficient. So people will prefer that. Now CO2 is just a working fluid here, and thermal energy system and a water system, they are just there to optimize the process. So if you want to improve the system, you have to improve both things, meaning the tanks also have to become bigger. If you want to have higher capacity, tanks have to become bigger, the dome has to become bigger, and thermal energy system also has to become bigger. Of course, water tank also to absorb that heat. So all these components can be scaled independently, meaning the generator and motor side can be scaled independently of the storage side, meaning these two variables are independent. You are like, hey, I'm just running a small village, very few people, but the solar is not that reliable. It only works like, we have a giant farm, but it's not very reliable. You're like, okay, we're gonna give you 100 megawatt hour capacity in terms of storage, but we'll only give you 1 megawatt output capacity. That's good enough. Again, that means it can work for a few days. So that can be done. You could be in a scenario where you have a lot of portfolio, where you have a lot of solar farms, a lot of wind farms, a lot of hydro, a lot of geothermal, all of that, but like stability can go YOLO. So tank size will be smaller, but generator side would be huge. You'll have tanks that are barely 100 megawatt hour, but the generators would be gigawatt hour. So you're like, I'm just balancing everything out. And one of the critical aspects why people really want this sort of system is that generator. Now you're like, why is that important? Well, think about this, like, why the heck you have 50 hertz? Or why the heck you have 60 hertz? And why the heck it's stable? Meaning you have many people turning things on, turning things off. How the heck it still remains at that? Like, there should not be anything possible to react to that fast, and we have been doing it from early centuries. How the heck we are doing that? Well, it's inertia. Think of it this way: when you think about steam turbine, you are thinking about something big, massive, like giant turbines. Then it has multiple stages of those turbines. So you are talking about a few hundred tons. Then you are talking about rotor, as in like things that are rotating inside the generator. That's also massive. Now you're talking about a spinning mass that could be 100 ton or even more than that, that is spinning. What does that mean? That means it has inertia. What does that give you? That gives you time. Meaning, if, for example, the generator capacity is 50 megawatt minimum, 100 megawatt maximum. Let's say it's producing around 50, but somebody turned on a big furnace. GG amounts of energy is now being consumed. Here's the deal. The motor will slow down. Again, energy cannot be created, not destroyed. So it will start to suck in. The magnetic flux will start to slow it down. But here's the deal. Because that was such a heavy thing that is spinning, it will take time. Now, what that time allows you? That time gives you computer time to like, hey, I'm supposed to be giving 50 hertz output. Now output is 49.998. Okay, I'm paying attention. 49.98. Yep, open up the steam valve. Now it will increase the pressure, so generator output goes up. Now that is a desirable thing. That's why our grids are stable. That's why we can have things where people are turning things on, turning things off without any issue. Same goes in the other direction, meaning if you have that furnace going YOLO amounts of energy consumption, generator maxed out 200 megawatt, 100 megawatt output, everything is awesome, but it turns off. Okay, it's like, yeah, I did my work, I'm turning it off. Wouldn't that go higher RPM? Inertia will still stop it. Inertia will not allow it to go from 50 hertz rotation wise to go like 5000. It won't. inertia will not allow you to change instantaneously. It will give enough time where computer will like, bro, why the heck my hertz are going from 50 hertz to 50.1? That means it's, load is going down. Okay, steam valves close down. That's how we maintain it. That's why you need spinning mass in our grids. Without it, it will be very unstable. And not to mention, everybody is putting solar inverters, everybody putting wind inverters. Those things are not spinning mass. That's very dangerous for us. And sometimes people are thinking of using giant condenser motor just for that sake. So instead of doing that, use this. It has generator, it has spinning mass, so it will stabilize the grid. So people want that. Like, this is one of those things where it's like, shut up and take my money. It is efficient, almost as efficient as a electrochemical system, and as robust as like a spinning mass system. Shut up and take my money. So workings is quite good. So what about the competition? Almost everything looks great if you do not compare it to anything else. So compared to compressed air energy storage system, far denser. Now you're like, this does not look huge. Here's the deal, the things are below it, underground, meaning it requires underground salt caverns where to store compressed air. Compressed air is 100% useless because it's not doing phase changing. Energy density, meaning how much cube meter you need to store any amount of useful energy, is idiotically huge. So it's very selective. Of course, if you are lucky enough, you have the place, awesome, GG. But most scenario you won't have it, so it's like very selective, useless. So when we come to cryogenic energy storage, that's really awesome. Does not require any selective things, anything like that. It's like, just put it there. And it's also denser. Be mindful, this puppy will give you high density, meaning if you have like, let's say 1 hectare of space, how much energy this puppy can pack in compared to CO2 batteries, this will be higher. Now, like, wouldn't that mean this is superior? Nah, this is an open loop system, meaning it's wasting energy every charging cycle. So fundamentally, if your energy pricing is not too high, like let's say nighttime energy is like very, very expensive, and daytime is very, very cheap because you are overproducing in daytime, only then you can justify economically this. Otherwise, people are like, yeah, this okay. Again, if your government is buying electricity for stability, they will pay whatever you want. If government is buying energy for growth purposes, that's different. So this has its uses, but not really that better compared to CO2 system, simply because of round trip efficiency. Then we come to pumped hydro storage. Now, pumped hydro storage is awesome. It does work. It's one of those systems that we know has been working for almost a century. It's one of those things like proven, tested, and awesome, but it does have very selective. It's very picky eater, basically, meaning you have to find a scenario where you have GG amounts of water, GG amounts of height variation, and all the subsequent infrastructure. This is also part that people forget. Just because you can see it in a satellite map, oh, this place will be perfect. You do the geotech. Do you have roads there to have like giant cement trucks going there? Do you have railway lines? Again, without railway lines, there is nothing that can transport that kind of material that is needed to make this. So these sort of structures take years to build. Yeah, they are, from cost point of view, they're amazing. It's just that their capital requirement is so high that people can't afford it. And even if you can afford it, do you have the location that meets all the criteria? Very rare. So far more flexible from this. So, and power and capacities are independent, meaning lithium ion is inherently limited. Again, if you make large amount of it, you do get some independence, but they are limited, meaning a lithium ion can only charge at 1 C. You cannot charge it faster than 1 hour, again, unless you want to destroy it. 1 hour is the charging time. 1 C is the most healthy time. And again, degradation is an issue. You cannot have like, oh yeah, this is a $100 billion equipment that I'm destroying because I'm speed charging it. This system is completely limited, meaning you can have a scenario where it's like, this is a 100 gigawatt hour capacity. I'm charging it in like, 15 days, no problem. I'm charging it in 1 hour, no problem. I'm charging in 15 minutes, no problem. It's independent, meaning two variables, how long your capacity is and how powerful that is, independent. Your tanks define your size of capacity, and your generators define the size of power, how much you have. So those things are very awesome, meaning your cities could have like a lot of power renewables pumped into it. It just needs something to stabilize it. Like, it's just like, dude, spikes are brutal, but we do not know. Like, we have things sorted out. It's just the spikes are brutal. It's like, I got this. You're gonna have very small tank, let's say 100 megawatt hour tanks, but your generators will be like 50 megawatt or 500 megawatts. It's like, I got this. So that is a very desirable thing. And as of now, doing holistic analysis of all the vectors, it's best of all the world, and it's very low cost, because while cryogenic energy storage does use things that are already in market, cryogenic temperature requires very selective metals. You cannot just put any metal in. The metal temperature required is 300 degrees Celsius in CO2 system. That's a lightweight temperature. That's like, even aluminum can is like, bro, I got this. You just put an insulator in it. So it's surprisingly far more effective. And not to mention, from an energy recovery point of view, hotter things are easier to recover energy from compared to cold system. So round trip efficiency also improves because of that. So what we can expect in the future? Well, reality is the need for energy storage is huge. At this point in time, there are a lot of wind farms, and if you can go to them, it's like, hey, put this puppy in, and you never have to turn off your wind farm ever again. They're like, shut up and take my money. And again, it's big, but not humongously big. It's like, it's big, but it's manageable. Like, there are many solar farms in India that also again have to curtail power output. They have to shut down basically strings of solar farms where it's like, bro, grid output is too going, frequency is going too high up. They're like, okay, shut it down. So they can just, instead of shutting it off, they can just, like, send that power into energy storage, and when the demand exceeds it during daytime, it's like, bro, I got this. Or if you are in a scenario where it's like small island grid where you can have like very large versions of this, so you can charge it from solar, wind, tidal, wave power, whatever have you, just charge that puppy in, and that power will stabilize everything else. And it also has spinning mass advantage, so it can black start a grid. And this is the common drawing that you're seeing, where you have tank sizes. That tank sizes will, again, be mindful, tank size is just not the dome. You also have to figure out the CO2 canisters. Then you also have to figure out the thermal energy storage system and the water tanks that are necessary for efficiency. Generators is completely up to your requirement. Generator and motor are the same thing, so that's up to you. Now, because of the fact that they are using everything that is in mass production, meaning you can pick up a phone and just figure out like, hey, can you build this for me? Yeah, the normal metal structure, no worry about it. Turbines, again, they're also specifying that turbines will last much longer, because turbines are generally running on very high pressure steams and very high temperature, 500 degrees Celsius temperature, and even some goes like as ludicrously high as like 1000. So they do not last very long, as in like they do last for centuries. It's just they require a lot of maintenance. Here, it's barely going to 300 degrees Celsius, so it's gonna last for a long time. So they're like, dude, if you go to ABB, it's like, bro, can you give me the turbine? They're like, yeah, take it, don't worry about it. You service it once in a while just for the lol sake, like you don't even need to service it. So it's really awesome. And quick commissioning means if India is building giant solar farm, India is becoming very fast at it. As in, like, we have achieved 1 gigawatt hour commissioning per day. We are getting fast. So if you're building giant farms, again, if it can be built in the same time, let's say it's a 2-3 years time frame for a giant giga farms that are like gigawatt hour capacity or more, that would be also awesome. Time is also money, so it's really awesome. But here's the, everything about it sounds too goddamn good. So I would be patient. I will wait for real world efficiency result, because everything about this does work on paper, on principle, on scale, by other metrics, it does work. It's just that what they're saying is the critical aspect is that efficiency. That efficiency where if they can touch 80%, at that point in time, just shut up and take my money. At that point, it's just like, shut up, take my money. Don't even think about it. Just shut up and take my money. So I would still urge caution, advisable some breaks, and then let's have a look, because that efficiency is the critical aspect. If they can achieve it, now be mindful, efficiency is one of those things that bigger you make it, the more efficient it gets. It's not going to be very easy to validate in 50 megawatt hour capacity. You can start to get some good results by 200 megawatt, really good results when you are touching gigawatt hour capacity, but we have to wait and see. Some caution is advised. So this was my presentation on CO2 battery energy dome project. Hopefully you have liked it, learned from it. In that case, please give the like button, share it amongst your friends. That will help me a lot. If you didn't like it, didn't enjoy it, I urge you to press dislike, press it twice to show me extra disappointment. Please leave a comment, because I do try to reply to all of them. Subscribe, press the bell icon if you're free, and as always, thanks for watching.